Hello, welcome to another session of this NPTEL course, Microwave Integrated Circuits. Today we are in week 3 of this course. In the last class, we had talked a lot about the various microwave theories, the techniques used. In this module, we are going to talk about a special class of parameters, circuit parameters that are frequently used in microwave engineering, and they are called scattering parameters. Now, we all know that there are various circuit parameters that are already well known. For example, the impedance parameters, the admittance parameters. But then all these parameters are dependent on the presence of voltage and current. In microwave engineering, we don't, let us say that voltage and current do not make much sense. One reason is because in single conductor waveguides, you cannot have a proper definition of voltages and currents. And in two conductor waveguides, they are very difficult to measure. So instead of voltages and currents, we tend to talk in terms of the incident and reflected powers. And S parameters are those parameters which relate the incident and reflected waves at the various ports of a microwave device. So let us see what these parameters are. Now, before moving on to the scattering parameters or S parameters, let us see what impedance parameters are. So I am sure this is well known, impedance parameters. If we say have an N-port network with various ports as shown, like this, then the matrix that relates all these voltages and currents to each other, it's called the impedance matrix. So if we can write down the impedance matrix, suppose we have this column matrix for all the voltages at the various ports, and say this is my impedance matrix. And suppose this column matrix is the currents, represents the currents at the various ports, then this matrix is my impedance matrix. So any impedance parameter Jij is defined as Vi upon Ij with all other Ik's equal to 0, K not equal to J. Now, similarly, in the same way that I defined the impedance matrix, I should also be able to define what I call the admittance matrix. So, once again, if we can go back to the slide, this is our N-port network with currents and voltages for the various ports as shown. Then the admittance matrix is defined as and any admittance parameter Yij is defined as where Vk is equal to 0, k not equal to j. Now, there is a concept of reciprocity. Various materials or various circuits are reciprocal. What it means is that if we have a network, see a network, we have some network, and if we apply some voltage at one part of the network and say in another part we get a certain I1, then reciprocity means that if we reverse this, that if we in place of this, if I suppose connect this resistor at this end and this source at this end, then I should be able to get the same current at this branch. So that is the concept of reciprocity. Now, in simple terms, reciprocity in terms of the z and y parameters that we just defined is that Zij is equal to Zji or Yij is equal to Yji. So, these are the similar, they are the same expression. So, it is not that both these have to be satisfied, any one of these. If any one of these conditions is satisfied, then the network is said to be a reciprocal network. And since this is the condition, I can also write it in a different way, that if my matrix, that is either my admittance or impedance matrix that I had defined, suppose this Z matrix, I call that represented by the capital Z symbol, then if this condition is satisfied, that is the transpose of Z is equal to Z, then again that implies that the circuit is or the network is reciprocal. So, with this, let us try to derive some properties of reciprocal networks. So, the first property that we try to I beg your pardon, let us try to derive some of the properties of a network for various cases like reciprocity and losslessness. So, for reciprocity, we already saw that the Z or Y matrix should be equal to its transpose. Let us see the condition for lossless. Now, the total complex power dissipated by an N-port network can be given by this relationship. So, this is the total complex power dissipated at port 1, V1 I1 conjugate plus half V2 I2 Here of course we are assuming that the V2 and I2 are the peak values, not the RMS values. That's the reason we have this half symbol here. So this is how we can represent it. Now if we suppose write an expression for Vn like this from the Z matrix, okay, then if we plug it back here, then what we get is that the P total is given by in the previous expression I by mistake had written this as Mn, this should be Nm. Okay, just I want to correct this. So then we know that for a lossless network, the real part of this P total is equal to 0. So then this implies that half of real so now okay, let me explain it in a different way. Suppose consider that only one of the ports currents are non-zero, okay, and let that port be called as N dash. Okay, so only the current in port N dash is non-zero. So if we now, so all other Im or Ins equal to 0 except N dash. So now if that condition is, if we plug that condition in this equation, then what we get is that for real value of P total to be equal to 0, we should have half of real N dash N dash I N dash I conjugate N dash should be equal to 0, and this implies that half of I N dash whole square now since I N dash is non-zero, so then only this thing should be 0. So in other, now look, this N dash can be any value. Now here this element is a diagonal element, Z N dash N dash. So what it means is that this particular diagonal element is 0, that is the real part of this particular diagonal element is 0, but then since N dash can be any value, any one of those diagonal elements, we have to conclude that all diagonal elements have their real parts as 0, that is they are all imaginary. So if only the network is lossless, then this is the condition, that all the diagonal elements are purely imaginary. Now, if we consider that this network is both lossless and reciprocal, then what happens? So, lossless and reciprocal. Now, consider that in addition to n dash, the port n dash, we also have another port n double dash where the current is non-zero. Okay. So, then if n double dash I n double dash is also not 0, then the condition of P, real part of the P total being equal to 0, that is the lossless condition, equates to once we have derived this equation, from there we can further because of the condition that all diagonal elements should be purely imaginary, from that we can simply extend that equation as this we could do, because if we go back to our expression for this, we saw that z n dash is purely imaginary, so is z n double dash, and these two terms, that I n dash conjugate and I n double dash conjugate, these are purely real. So, then this whole term is purely imaginary, hence the real part of these, the sum of these two terms, that is this term and this term, will be 0, and only this term and this term will be remaining. So, that is what we have kept here, only the remaining two terms. Now, since this is also a reciprocal network, we have defined our network like that, hence z of n dash n double dash should be equal to z of n double dash n dash, and this condition, if we apply to our circuit, translates to now this term is purely real, just like the other two terms. These two terms are purely real. Since the real part of this whole term is equal to 0, hence this term must be purely imaginary. If this term is purely real and the whole real part of this expression is 0, then this term has to be imaginary. If it is real, then it cannot be 0. So, then we conclude that z of n dash n double dash is also purely imaginary. Therefore, for lossless and reciprocal network, we have that all the elements in the Z or Y matrix are purely imaginary. So, in summary, we can write it like this. and if the network is both reciprocal and lossless, so now we have analyzed our network for with respect to the concepts of impedance and admittance parameters. Let us now go to the next and the main topic of our discussion here, which is the scattering parameters. Now, scattering parameters, as I said, have several advantages. One is that they have the concept of power. So, let us go back to that N port network which we had talked about earlier. Now, we also know that the normalized voltages or currents at the various ports are given in terms of the incident voltages as follows, where Vn and Vn minus, the sum of them is equal to the total voltage at the port, and this we can also write in terms of An and Bn. And then we also know that the normalized voltages at any port is given in terms of the actual voltages as shown. So then this can simply be written as An plus Bn. So then with this in mind, we can also then jot down the formulae for the current. The current, as we know, is given by and then the normalized current is given as this. We can also have an expression for the normalized impedance matrix. Just like we have normalized voltages and currents, the normalized impedance matrix can be given like this. So, any particular element in this normalized matrix is given like this. So, then we can see the input and output or the incident or reflected waves are given as Bn's and An's. Now, if we write a matrix relating the B's to the A's like this, so these are the values. This column matrix represents the reflected, normalized reflected voltages or normalized reflected currents at the various ports, and say at the other end we have another column matrix representing the incident normalized voltages and currents or currents, then the matrix that relates the two is called the S matrix. So we see that just like the impedance and admittance matrix, this is also a matrix that relates two circuit elements or two circuit parameters. Of course, here the circuit parameters are defined in terms of power rather than voltages or currents. And the other difference that we will see in a moment is that these parameters, these circuit parameters, these S parameters or scattering parameters are also dependent on the characteristic impedances Zn. So, if we want to define a particular S parameter, then the definition, the formal definition of Sij is with Ak equal to 0 for k not equal to j. Alternatively, we can also define it as now. Two-port networks are very popular. Since two-port, in fact, two-port networks are the most widely used microwave components, both for passive as well as active circuits. Some examples of two-port passive circuits are filters, then attenuators, and for active circuits we have amplifiers, which are also two-port circuits. So popular are these networks that we have some special names for the two-port S parameter matrices of the elements of the two-port S matrix. So, for a two-port network, we can write the B's and A's as B1 is equal to S11 A1 plus S12 A2, and B2 as S21 A1 plus S22 A2, and these B1 and B2, if I write it in the form of a matrix, so we have a total of 4 S parameters for a two-port network. These two-port networks, these parameters, I can just write down like this, equal to B1 upon A1 with A2 equal to 0. This is B1 upon A2 with A1 equal to 0. Then this is equal to B2 upon A1 with A2, and this is this is S22 B2 upon A2 with A1 equal to 0. This parameter, this S11, is known as the input reflection coefficient. This is S12 is known as the forward transmission coefficient. S S21, sorry, this S21, I beg your pardon, is known as the forward transmission coefficient. S12 is known as the reverse transmission coefficient. And S22 is known as the output reflection coefficient. Now, we have certain special properties for these S parameter matrices. Just like we derive the conditions or the two-port for the Z parameters and the Y parameters, that is under when they are lossless or reciprocal or both lossless and reciprocal. Similarly, for these S parameters also we can derive certain conditions, and that we shall derive in the next module. Thank you.